so let's go ahead and get started. So I have a short announcement, and then we'll talk about learning catalytics, or course networking, that is. So I talked with the other professors about the syllabus quiz and some of the assignments that were due on Tuesday. Some of you hadn't completed them because you weren't, I guess, in the habit of going and checking things. So what we're going to do is we're going to give you some retrieval there. So if you haven't completed those assignments for the syllabus quiz, take the syllabus quiz online. If you didn't complete one of the homework assignments, I'll take them until next Tuesday if you just write them by hand and then you turn them in to me. Okay, but those are only the assignments that were due Tuesday, so anything after that, we should know at this point that we're going to have homework due. Okay. The other thing concerns course networking. So we did try to lay out more stringent rules for the things that we wanted you to do, but asking for solutions is not really one of them, right? So if you're working on a problem, share what you're doing with the other students and say, hey, I'm working on this, and this is what I've gotten so far, and it's not making sense to me. Has anybody else been doing this? Don't just ask, hey, I'm having trouble with 3 or 4 problems, and then say what are the answers to them, because that kind of defeats the purpose of what we're trying to do. We really want you guys to be discovering the answers yourselves and learning how to do them, because ultimately that's what we want you to be able to do, and that's what you're going to have to do on the test. So remember that video I had of the commencement that Neil deGrasse Tyson gave. We want you guys to learn how to think and not just know what to think, and in doing that and getting you guys to think about problem solving, we're trying to help you develop those kinds of skills that are really transferable to other fields as well. So if a lot of you guys are going to go to medical school, you're going to have to be, you look at a situation and say, hey, what's wrong here? You can't just, pull out an answer that was written on a test or something, or ask somebody, what was the solution you got to this? You can talk to your colleagues and say, hey, I'm having this problem, these are the things I'm thinking about. Think about the context of the problem and discuss it, and then come to a solution. But you're not really going to be doing yourself or your patients any favors if you're just asking other people for what the solution to a problem is and figuring it out yourself. Okay, so with that, we're going to continue on today with electric fields and move into Lorentz force law and ultimately get to the electric potential energy. So just to start out, we're going to come back to that question that we ended with last time, so I won't leave you guys hanging on that. But just to get us going, I have a couple of questions on learn catalytics, so you can fire that up. Okay, so let's go ahead and talk about this one, and if you haven't put an answer, and you can put it in. So what do we think? What do you guys think? You have any ideas?
The same.
The same. Why are they the same?
Because the electric field lines are directly proportional to the charges.
Right. So the amount of electric field lines, or like how big they are, is going to be directly proportional to the magnitude of the charge. And if we look at these two setups here, we can count the lines. This one has 8 lines and this one has 8 lines, and they're all roughly the same size. And so the magnitude of these charges is going to be the same. But what's going to be different? The direction, the direction is going to be different. So what does that indicate? Yeah, they have different charge, right? So if I'm looking at these two, one's going to be one thing and one's going to be another thing. What are those two things?
Positive, negative.
Positive and negative, right? So which one's going to be the positive charge? My left. You're right. Yeah, A. Okay, and then that leaves B being the negative charge. Okay, good. Let's move on to the next one. So in this one, I give you a whole bunch of setups of charge, and what I want you to do is I want you to pick all of the positive charges. All right, so what did we say? What did we say about this one? Don't be shy. A lot of guys, I heard you had the right answer, right?
Yeah, ACFGHI.
ACFGHI. Good. And so you can do this one of two ways. You can look and say which ones are the positive charges and just check those ones, which is ultimately what you have to put in. Or you can look and see which ones are negative, and all the ones that are negative are not the right answer, right? And so we can see that the ones that we just said are going to be radiating outward, and all the other ones are going to be inward. Now, I had a question about, well, why is it that we know that positive charges radiate outward and negative charges are inward? So there's two ways to think about this. I'll first start by talking about the equation and how the equation can tell us that that's the right answer. And then I'll talk about the more conceptual way to think about it in terms of test charges. So in terms of the equation, we remember that whenever we're defining this unit vector r hat, by definition it points from the charge to the other charge, or let's just leave this as an arbitrary charge, let's call this q. It points, in the case of the force, it points from one charge to the charge I'm finding the force on. Or in the case of the electric field, it points from the charge to where I want to find the electric field. Okay? So this I've left arbitrary right now, and I've drawn in the unit vector r hat, right? R hat this is where I want to find the electric field here, so I want to find it here. This is going to lead into some of the calculations we're going to do too, so this is important. So if I want to find the electric field at this point, the unit vector points from the charge to that point where I want to find the electric field. Now, the way that I've been taking care of the negative signs here is I assign a charge here. I can say that this is either a plus capital Q or this can be a minus capital Q. Now, if it's a plus capital Q, I plug that into this equation. This is K plus Q divided by r squared times r hat. And this is going to be positive, which means that it's still going to be going in this direction, right? The same direction that the unit vector points from the charge to where I'm finding the electric field. Now this is times, it's not K plus Q. Now if I plug in the minus Q, this is equal to K times minus Q. Now we see something kind of interesting, right? Because now this negative sign changes the direction that this points. And so now this one points towards the charge, okay? So that's one way to think about this. The other way to think about this is the conceptual way in terms of test charges. And that's to say, if I have some arbitrary charge here, Q, and I put a positive charge over here, what's the direction that this charge is going to go, this positive Q? Well, without telling you what this one is, I don't know yet, but if I say that this is a positive Q, what's the direction this one's going to move? It's going to move away, right? So if this is positive and this is positive, this is going to move away. So this is the direction that the force is going to act on this one. Now if I do the same thing, so say I have some arbitrary Q here, and then I put, again, a positive test charge here. But now this one's going to be a negative Q. What's the direction that this one's going to go? It's going to go in, right? And so that's the other way that we can think about the direction of the electric field lines, okay? So does that answer your question? Okay. Any other questions about this? Because this is actually a very important point when we're doing our calculations, and we're going to be seeing some more of those calculations later today. Okay, no questions? Okay, so let's move on to the next and last one. Now we have this setup. So now how do the magnitudes of these charges compare? And we could also say which one might be positive or negative, or if they're both positive, both negative. Good. So I think I'm going to have to start asking harder questions to you guys because these are a little too easy. But well, I say that, and I know already I'm going to be asking harder questions. So I'm glad you guys are happy with me now. Hopefully you'll stay happy with me. So what do we say? A says that charge C is the magnitude is greater than charge D. Why? So somebody all the way in the back over here. What do you guys think? Why is the magnitude of charge C greater than the magnitude of charge D?
There are more lines pointing outwards away from the charge C than there are towards.
Exactly. So if you count the number of lines here, and I don't know if I have enough fingers, so I can't do that, but you can see almost immediately, right, that C has more lines radiating away from it than D has lines coming towards it. So that means that the magnitude of charge C is greater than the magnitude of charge D. Okay. So that's actually going to be it for our learning catalytics for the day, so you guys can put those away. The rest of what we're doing are going to be calculations. So this is the same calculation that we didn't quite finish last time, but this is where we left off last time. So we know that we have these two positive charges here and this negative charge in the top right. We want to find what the electric field is at this point down here. Okay. So look back at your notes from last class and continue doing that calculation. And I'll give you guys maybe about 10 to 15 minutes to do this one. If you haven't finished, that's okay, because we're going to move on to another one, and you're going to get more practice with these. I think that the hardest part of this that I saw as I was going around is finding the electric field from this one, right? The other two are pretty easy. It's finding this one. So let's go through these two quickly. And actually, if you're clever, you realize that you only really need to do one calculation, right? So let's first look at the electric field from 2. And first, as always, we should write our primary equation somewhere at the top of the page, so we know where we're starting from and we know what equation we're using. So this is E is equal to KQ over R squared times R hat. Now when I want to look at the one from 2, E vector 2 is going to be equal to K times Q2 divided by R squared. This is going to be a distance of 0.04 meters here. So this is 0.04 meters squared times R hat. Now R hat for this one, always by definition, R hat points from the charge to where I want to find the electric field. So what's that vector? What is this R hat? What's the vector that points from here to here? It's going to be y, yes. Negative y, right? Because if I have my coordinate system drawn here, this is the plus y direction, and this is the plus x direction. And so this points from here to here in the minus y direction. Now we also need to plug in our charge here and also plug in k so we can finish the calculation. So this is minus y hat. So this is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared times, this has a charge of 2 microcoulombs, but it's also negative. So this is minus 2 times 10 to the negative 6 coulombs divided by 0.04 squared times negative y hat. And so what we see with the way that we chose our R hat and our Q in this method that I called method 2 from the first or second lecture, that this ends up resolving itself in the direction that we expect it to, right? So we know this is a negative charge, and the electric field from this one always has to point towards this. So that for this should be in the plus y direction, and this becomes plus y. Now when we plug in our numbers for this, what we end up finding is that this is equal to 1.1 times 10 to the 7 newtons per Coulomb in the plus y hat direction. Okay? not too bad. Now, like I said, if we're clever, we can look at charge 3, and without really doing any calculations, we can write down what the answer is. Because I know that all of these charges have the same magnitude, and I know that this one is the same distance as this one from this point, right? So to write down what E3 is, I can take this answer and I can just write it again. 1.1 times 10 to the 7 newtons per Coulomb, and then just put the proper direction here, right? This is a positive charge that points this way, and so this is going to be plus x hat, right? So far so good, right? Any questions about what I've done here? Okay. So now we get to the tricky part, and that's going to be to find what the force is from what the electric field is from 1, okay? So E1 is going to be equal to K Q1 divided by R squared times R hat, right? Now to write R hat, this is the direction this is going to point, right? I can put in an angle here, we can call theta, and that's going to be the same angle that I have here, theta. And as I've done before, we can blow up this portion, and we can look at this in a little bit more detail. So this is going to be, this is theta, this is R hat, and then this is going to have some part in Y and some part in X. So to write R hat here, we say that this is going to be something times X hat plus something times Y hat. So given that angle that I have here, what is the something times X hat? Sine, cosine, tangent, cotangent, cosecant? Sine, or well, here it's going to be cosine, but ultimately it ends up being the same, right, because of the angle. So this is cosine. How about this one? This one's a little tricky. It's going to be sine, right? Are we happy with this? Yeah? No? Yes, it should be minus sine, right? Because remember, this was the coordinate system that I chose. Plus y is this way, plus x is this way. This is in the plus x direction, but it's in the minus y direction. And so I need to make sure that I include that negative sign. Now, because I know theta here is 45 degrees, how do I know theta is 45 degrees to start with? Because the sides are the same, right? This is 4 centimeters, this is 4 centimeters, so the angle is 45 degrees. I can evaluate this, and so I know cosine and sine of 45 are the same thing. It's root 2 over 2, or 1 over root 2. So this is going to be root 2 over 2 times x hat minus root 2 over 2 times y hat. Now, we need to plug in the rest of the things that we have here. We also need to find what r is. So how are we going to find what r is, or r squared? It's always the same thing we do to find r, right? Pythagorean Theorem, right? So we know this is r, this is what we want to find, and we know what these sides are, right? We know this is 0.04 meters, this is 0.04 meters, and so this is 0.04 meters squared plus 0.04 meters squared, which is equal to 2 times 0.04 meters squared. Okay, so let's plug everything in here. And so then what we have is E vector 1 is equal to 9 times 10 to the 9th newtons per Coulomb squared meter squared times the charge. Now is this a plus charge or a minus charge that I'm calculating from? Plus charge, right? So I put in a plus 2 times 10 to the minus 6 coulombs divided by 2 times 0.04 meters squared, and then this is multiplied by root 2 over 2 x hat minus root 2 over 2 y hat. Okay? Now, when I plug this into my calculator and I evaluate it, what I end up finding is that E vector 1 is going to be equal to, this is 3.9 times 10 to the 6 newtons per Coulomb in the x hat direction, minus 3.9 times 10 to the 6 newtons per Coulomb in the y hat direction. Okay? And we can, yeah?
How did you evaluate that?
So what I did is I did it one at a time. So, and actually, when you look at this, you realize what you plug into your calculator is going to be the same regardless. And you see that it should come out that way, right? Because this is 45 degrees, whatever happens in x happens in y exactly. So what I can do is I can take this multiplied by this, divided by this, multiplied by this, times root 2 over 2. The x hat and the y hat, they aren't things that you plug into a calculator, right? Those are just labels to indicate that this is going to be an amount in the x direction and an amount in the y direction. And then once you do that, you end up getting this. Okay, does this make sense? Okay. So then, in the end, when I add this to what I had found for the electric field from 2 and 3, this gave me that the total electric field, E total, is 1.5 times 10 to the 7 newtons per Coulomb in x hat, plus 7 times 7.0 times 10 to the 6 newtons per Coulomb in y hat. Okay? And that's it. Who was able to get this exactly? Okay? Yeah, quite a few. So if you didn't, that's okay. We're still practicing, right? We'll get it in due time. So let's move on to the next one. Yeah, question. Sure. So this was E total is going to be equal to E1 plus E2 plus E3, right? Right? And so to write this very explicitly, what I can do is I can write out all of the components of E1, E2, and E3. So E1 was 3.9 times 10 to the 6 x hat, minus 3.9 times 10 to the 6 y hat. So this is E1. E2 was, and I'm going to be very explicit here, so when I add it, it's very clear. This was 0 in x hat, right? Because E2 was the one, it was the negative charge, right? It didn't have any x component. So it was 0 in x hat, plus 1.1 times 10 to the 7 y hat, and these should all be multiplied by newtons per Coulomb. I'm getting a little lazy with my units, but these all have newtons per Coulomb. And then E3 is going to be 1.1 times 10 to the 7 x hat plus 0 y hat newtons per Coulomb. And then when I add them all together, that's how I got this here. And when I add these vectors, I have to add them component by component, right? So the x components are added together, and then the y components are added together. Okay. So I apologize if I went a little bit quickly through how I did that, but I hope that makes more sense. Is that better? Okay. Any other questions about this one before we move on? It's okay if you have questions. This is the time to ask them, because we want to make sure we understand this. Yeah?
We don't include root 2 over 2 in the final.
No, that got multiplied in here. That got multiplied in here. So you could, if you wanted to, calculate exactly what this is and then say it's multiplied by root 2 over 2, and then that would be what you had here. But I made that part of the calculation when I calculated the component. Yeah. Other questions? Yeah.
So I understand like the adding the vectors up did finally, but I don't get how 3.9, the negative 3.9 plus 1.1 gets you 7.
Times 10 to the 6.
Oh, okay.
Yeah, so this is like 11 minus 4. Yeah, good. Other questions? Go on, try something. Yeah. Yeah.
So for the square root 2 over 2, I keep doing it over and over. I keep getting 3.5 in my calculator.
When you find what cosine of theta is, or
I did like the stuff on the left, like the 9 and then the 2 and then the stuff on the bottom. I did all that and that came up to 5 times 10 to the 6. And I multiplied that with the stuff in the parentheses and that had given me 3.53. Is that just a rounding error, or is that?
what you got here was 5.3?
3.5.
3.5, it probably is. Yeah, it probably is. Yeah. Other questions? Okay, so a little louder. That's a very good question. The answer is no. The answer is no. And that kind of takes us to the next one. Okay, so we'll see in the next one. Okay, so now we're going to be doing this. So really, I mean, you look at it and you say, oh, this is terrible, but really it's just doing what I just did twice. Okay, and then after that, the question after this, you're going to do it 3 times, and then 4 times, and then 5 times, until you know it. No, I'm kidding. This is the last one of these. This is the last one of these. All right, so let's go ahead and talk about this one. So this is really kind of just more practice with what we had on the last problem that was kind of the hard part, right? Finding what the components of electric fields are when they're at angles. So we want to find what the electric field is at this star here. And so what that means is we need to find individually what the electric field is from Q1 and what the electric field is from Q2, where Q1 is going to be -2 microcoulombs and Q2 is going to be 1 microcoulomb. And this is going to be positive. Okay, so to find the electric field from 1, this is going to be KQ1 over R squared times R hat. Now we just need to figure out what this R hat is. So R hat is going to be equal to some blank times X hat plus some blank times Y hat. And with the method that we're applying here, we say that by definition R hat points from here to here. So what's the part that is in X for 1? Cosine of 25, right? And the part in Y? Sine of 25. And we know that this distance R is just this distance A, which is going to be 0.02 centimeters. Okay. And so we just plug everything in, right? So this is going to be equal to 8.9 times 10 to the 9 newtons per coulomb times the negative charge -2 times 10 to the -6 coulombs divided by 0.02 centimeters squared times whatever cosine of 25 and sine of 25 are. You can plug those into your calculator. And when we do this, what we end up finding is that E1 is going to be equal to minus 4.0 times 10 to the 7 newtons per coulomb and minus 19, or minus 1.9 times 10 to the 7 newtons per coulomb. And this is multiplied by X hat, and this is multiplied by Y hat. Okay? So to get the electric field from 2, we're going to do exactly the same thing. So E2 is going to be equal to KQ2 over R squared. So we need to find what R hat is and what R is. So in this case, R hat, again, is going to be something times X hat plus something times Y hat. And as always, by definition, R hat points from here to here. So what's going to be the X part? Should be getting pretty good at this, right? Should be cosine of 15. And then the Y part, sine of 15. Are we happy with this? No. I'm not happy with it either. What's wrong? I need a negative sign, right? This x component points in this direction, and by convention, we say that this is the plus x direction, this is the plus y direction. And so this is going to be in the minus x hat direction. Is my y okay? Yeah, y is fine, right? Because y is positive here, and it points up, right? Okay, so here r is going to be equal to 3.27 centimeters, so we can plug all of this in. So this is going to be 8.9 times 10 to the 9 newtons per Coulomb squared, meters squared. Ooh. Nobody caught me on that one. Okay. This is times 1 times 10 to the minus 6 coulombs divided by 0.0327 times minus cosine of 15 times x hat plus sine of 15 times y hat, okay? And when we plug that into our calculator, we end up finding that E2 is going to be equal to negative 1.6 times 10 to the 7 newtons per coulomb in x hat, and 4, I can't read my own handwriting, plus 4, let's say this is 4.5 times 10 to the 6 newtons per coulomb in y hat. Okay, so now to find what the total electric field is, so this is what we calculated. We calculated E2, we calculated E1, and we want to add those two vectors together to find E total. So when we add those two vectors together, because we've written them in components, we can do that pretty easily. We just add the x parts to each other and add the y parts to each other. We end up finding this is equal to minus 5.6 times 10 to the 7 newtons per coulomb, and minus 1.5 times 10 to the 7 newtons per coulomb in the x hat direction and the y hat direction. Now, you might have something a little bit different because of rounding, and I think I was a little cavalier with my own rounding, but you should find something that's about 5.5 times 10 to the 7 and about 1.5 times 10 to the 7. Yeah, what's up?
I was wondering why, for E1, why does the negative charge, like, it doesn't attract it, it like repels it? Like the negative charge on Q1.
This right here?
Yeah, why is the cosine and the sine positive?
Okay. Because by definition, for the convention that I'm using, r hat always points from this point to this point. And so that direction that it's pointing is this way. Now, how that gets fixed is because of the fact that I'm plugging in exactly what the charge is, the value of the charge. So that negative sign flips it. Okay. So you just have to be careful. I've been consistent with the way that I've been presenting this. And this is my preferred way to do this. You could also do it just in terms of magnitude and say, okay, well, what's the magnitude of this? Take the magnitude of this, and then when I determine the vector, say that the vector points in the direction the electric field should point, and that takes care of it. Yeah. Other questions? Okay. So I think we're getting better at these, right? And getting a little bit more comfortable with them. So now, a horse of a completely different color. So this is using another equation that I have written up here that we haven't used very much at all yet. Oh, also I should remind you of some equations that we had last semester. So what do we need for this? We need Newton's second law. we also need, and this one. So I have this box and I have this electric field in the box that I have described here. What's it going to look like? It's going to be that way, right? So I'm going to have all of these lines here representing the electric field in this region. And if these should all be the same length, right? Because it's a uniform electric field. Okay. So imagine I'm good at art, okay? And these were all the right size. So then what we want to do is we say, okay, well, I'm going to plop some charge in here, just some positive charge. And I want to find what the force is that acts on this, okay? So in order to do that, we have an equation here that I talked about a little bit last time. This is the electric portion of the Lorentz force law. And what this says is that the force acting on a charged particle in the presence of an electric field is just going to be equal to the value of the charge times the electric field vector. Okay, so let's see how that works here. So I tell you that I have an electric field of 3.5 times 10 to the 4th Newton per Coulomb. So E vector is equal to, I just read it and I forgot, 5.3 times 10 to the 4th Newtons per Coulomb in the positive x hat direction. And I have a charge of Q is equal to 2.8 microcoulombs. So I want to find the force. I can just plug these things in. So this is going to be equal to, and again, I'm using the convention that when I'm plugging things in here, I'm plugging in the positive charges, right? And you'll see what's going to happen with the negative charge. So I plug in positive 2.8 times 10 to the 4th Newtons per Coulomb. And then this is multiplied by what did I just do? Oh, this is. You guys will forgive me. It's Thursday for me too, right? So this is the charge, and then we plug in the electric field. So this is 5.3 times 10 to the 4th Newtons per Coulomb, and so this is going to be equal to 1.4 times 10 to the minus 1 newtons. Okay. Now let's see what happens if instead of a positive charge, I put in a negative charge, where this negative charge is going to be equal to, this is going to be equal to negative 9.3 times 10 to the 6, 10 to the negative 6 coulombs. Okay. So do the same thing. Say F is equal to minus 9.3 times 10 to the minus 6 coulombs times our electric field, 5.3 times 10 to the 4 Newton per Coulomb. Erase some of the mess that I left from last time, and then when we plug this in and evaluate, now I lost my vector signs here. You guys should yell at me for that, because I had a vector on this side, I didn't have a vector on this side, so we need to keep our vector signs. And so when I plug this one in, and again plug in our negative charge, this is going to give me minus 1. No, I'm looking at the wrong. Minus 4.9 times 10 to the minus 1 newtons. Okay, so let's look at these two answers briefly and see that I have this electric field. I put a positive charge in it. Does the positive charge go with or against the electric field? With. Goes with it, right? I'm just going to go that way. Negative charge, what does that one do? It goes against it, right? Because if I had a negative charge, it's going to go the opposite direction as the electric field. And so we can see that very explicitly in the calculation using the Lorentz force law, that the vector F and the vector E are going to point in some direction, and whether Q is positive or negative will make it the same direction or it'll make it the opposite direction. Okay? And we're going to skip the other part because I wanted to, in the last couple of minutes, talk about this next one, and then I'll lay out some equations. Actually, I'll probably lay those out next time. Actually, yeah, take the last 5 minutes to talk about how we can solve this one. Okay, so let's, I'll let you guys go a little bit early today, but I do want to talk about this one. So, how can we go about this one, considering what we just talked about? How could we figure out what the velocity is of this Q2? We have Q1 fixed. We know this is going to repel it. How could we do it? Yeah.
Potential energy and then it has potential energy at the end and
That's one way to do it, yeah. And ultimately, that's kind of the better way to do it. What do you think?
We need to get E first, then we can get F from F equals MA.
Yeah, that's the other way. So the two ways that you could do this are either to use conservation of energy, or we can use Newton's laws, right? We know now how to calculate the force on a charged particle in the presence of an electric field. And if we wanted to do it like that, just for fun, I'm going to show you guys what it would mean to try to do that, and why we're not going to do it like that. So, if we start with Newton's laws, we say that the sum of the forces is equal to the mass times the acceleration. The force that acts on this one is going to be Coulomb's law, so this is going to be F is equal to K Q1 Q2 over R squared. We know this points in the R hat direction. Now we can just make this equation one-dimensional by saying then that MA is equal to K Q1 Q2 over R squared. Now, the thing about A is that A, in terms of units, what is it? Meters per second squared, right? R is units of meters. These two have to be able to talk to each other. And so we know previously that A is equal to the change of velocity over a change in time. And V is equal to a change in position divided by a change in time. So if I really wanted to solve it like this, well, first I need calculus. So let's hop in and do a little bit of calculus here. So we have m d second x dt squared is equal to k q1 q2 over r squared. And this is an r actually. You want to show them how to solve this one? No? This is a really nasty equation to solve, and nobody would want to do this, which is why we opt to use conservation of energy instead. Okay? So we're going to come back to this, and we're going to put all of these things together. We just talked a little bit about potential energy. We're going to talk about how that comes together with Coulomb's law and our definition of the point charge electric field. So you guys have a good weekend.